Hi, I'm Bohus. I'm a researcher in the Perception and Interaction group in Microsoft Research in Redmond, and my work focuses on multimodal and physically situated interaction. Basically, the main question that drives my research agenda is how can we get machines to reason more deeply about their surroundings and participate in interactions with people in the physical world. Now, today, however, in this webinar, I'd like to talk to you about infrastructures. And specifically, I would like to introduce you to Platform for Situated Intelligence. Now, this is an open source framework we've developed recently at MSR that supports development and research in multimodal integrative AI systems. I'm going to clarify in a second what exactly I mean by these terms, multimodal and integrative AI, and what is the actual scope of the framework. But before we get going, I would like to say that while I'm giving this presentation and two of my colleagues, Sean Andrist and Ashley Feniello, will be joining me for the live QA session that follows, this is a work of a broader team of engineers and researchers, and I would like to list and thank and acknowledge all of them right at the start. Okay, so Platform for Situated Intelligence, which we sometimes abbreviate as \PSI and pronounce like the Greek letter psi, is an open source framework that simplifies development and research in multimodal integrative AI systems. These are systems that leverage different types of streaming data, such as audio and video and depth information, and that integrate and coordinate multiple types of AI technologies to basically process this data in real time. So a prototypical example in this space might be a robot that uses cameras and microphone arrays to try to understand the world around it and engage in an interaction with coordinated speech, gaze, gesture with multiple people to, for instance, give directions inside a building. Building a system like this obviously requires a lot of multimodal audio-visual processing and leveraging different kinds of AI technologies. Speech recognition, computer vision, dialogue models, behavioral controllers for gestures, so on and so forth. Now, this system is at one end of the complexity spectrum, and Psi as a platform was developed in part to support development for this kind of rich multimodal systems that do a lot of intensive processing and have many different components. At the same time, the scope and reach of the framework is actually much broader. Basically, anytime you are dealing with temporally streaming data, or if you need to bring together multiple kinds of technologies, and especially if you're in a situation where you're latency constrained or where acting in real time matters, the affordances that Psi provides can accelerate development. Over the last years, we've seen a lot of fast progress with machine learning in a lot of perceptual AI technologies. However, building end-to-end useful systems of this nature is quite a daunting engineering task. And in part, the problem lies with the fact that the fabrics and programming languages that we use to build these systems are missing important primitives and are not really well attuned to this type of task. So Psi as a platform was developed to address these challenges and simplify development for this type of systems, whether they're social robots interacting with groups of people in public spaces, intelligent buildings, instrumented meeting rooms, mixed and virtual reality systems, all the way to applications that use simpler, smaller devices like a Raspberry Pi or some IoT sensor, but that still do stream processing. So now that hopefully we've clarified the scope of the framework, let's talk about the outline of the rest of the webinar. So I will start by discussing some of the challenges with building these kinds of applications in a bit more detail. After that, I want to give you an overview of the main aspects of the framework to get you familiarized with some of these principles and tools and affordances, and for you to get a sense about whether this would be something that might be useful in your own work. Following this overview, we'll do a bit more of a deeper dive into actual coding. I want to do a hands-on tutorial and show you how you might write a first application with this. And again, we won't have a lot of time to go into the detail, but the idea is to give you a feel for what programming with Psi is like, and for you to be able to understand whether this might be something useful, again, in your own work. The tutorial will take about 30 minutes. At the end of that, I will give you more pointers to some documentation and resources. And then I want to bring the conversation more to how you might get involved. As I mentioned before, Psi is an open source framework, and we're looking forward to really creating a community here and getting more people engaged to help us bring this to the next level. And at the very end, we'll have a live Q&A session. Okay, so let's get started from the challenges. Well, to a large degree, many of the challenges with building these systems stem from their multimodal and integrative nature. These systems work with different types of streaming data, so audio, video, depth, LiDAR, pose tracking results, speech recognition results, so on and so forth. This data is generally streaming at different bandwidth and with different latencies. And it's typically processed in these complex pipelines that bring together many kinds of components built out of heterogeneous technologies, right? You might have anything in these pipelines from, sensor-specific device drivers to cloud services that induce a certain amount of latency, to deep networks that run on GPUs and other kind of GPU processing, to application-specific logic and code and interaction with databases, so on and so forth. Now, these systems tend to be pretty compute intensive, and they often need to operate under latency constraints. And so performance considerations are quite important. Oftentimes, you want the systems to behave well under load or under latency, and properties such as graceful degradation of performance are often a requirement. Now, even if you leave aside the challenges that stem from the sheer complexity that these systems have, and from the fact that they use these heterogeneous components and they have these stringent performance requirements, a number of other challenges arise from the fact that the programming languages and the fabrics that we use today are missing an important set of primitives, are not well attuned to these kind of applications. For instance, notions such as time, space, and uncertainty are core in a lot of these systems, yet these are not first-order objects in any of our programming languages today. And as a result, a lot of time ends up being spent developing low-level infrastructure issues. Take, for instance, time. I've already mentioned that these systems need to be fast, but being fast is not enough. Coordination actually requires being latency aware. Oftentimes, these systems need to perform data fusion, where a component needs to integrate information coming from different pathways. Well, to do this correctly and in a reproducible manner, the information arriving on these different streams needs to be paired according to when those events happened in the world, not according to when they reach this component, because that might be affected by latencies in the system and so on. And so in the absence of the right primitives, a lot of efforts ends up being spent on building this kind of infrastructure and debugging low-level issues rather than on the task at hand. Finally, I would argue that these applications also have a specific set of needs when it comes to debugging and data visualization and analytics, which are not sufficiently addressed by the development tools that we have today. So for instance, debugging these complex concurrent applications with breakpoints and printfs is not really scaling, is not really effective. At the same time, other aspects such as data visualization, the ability to inspect and visualize these data streams as they flow through the application, and the ability to run queries and perform data analytics can significantly speed up the development cycle. So Psi as a platform was basically built out of a desire to address these challenges and basically to provide the right kind of infrastructure and tools and components to accelerate development for this kind of multimodal integrative AI applications. The main goal of the framework is to lower the engineering costs basically and foster more innovation and research in this space. And we're open sourcing this framework because we believe success in this space really hinges on building a community, on bringing together expertise and know-how from different areas, and ultimately on building a thriving ecosystem where we can leverage each other's work. The framework is cross-platform, works both on Windows and Linux, and it's built on .NET standard. So it's a managed framework that retains the affordances of a managed programming language like C#, so things like managed memory and type safety and so on, while aiming to address the performance requirements that these applications often have. At a high level, Psi provides three kinds of affordances. The Psi runtime provides infrastructure for working with multimodal temporally streaming data, and it provides a parallel coordinated computation programming model that simplifies writing applications and components in this space. There's a set of tools that are centered on data visualization, annotation, and data processing and analytics that accelerate the development cycle. And finally, the third part is an ecosystem of components that wrap different technologies and allow you to quickly prototype and foster reuse. So over the next few slides, I'd like to give you a brief overview of each of these areas. And I'm going to start by talking about how Psi applications look like and what are some of the affordances that the Psi runtime and low-level streaming infrastructure provide. So Psi applications basically are pipelines or graphs of connected components that talk to each other via streams of data. I have a fictitious pipeline here where there's a microphone and a camera. Let's say you're trying to detect who out of many people in an image is the one talking. So you take the audio from the microphone, pass it through a voice activity detector that tells you that speech is happening. Similarly, the images from the camera run, let's say, through a lip movement detector, and then you try to put these two signals together to figure out who is talking, who is the speech source. Now, writing these kinds of applications, wiring components together, is very easy to do inside. The code on the left-hand side kind of illustrates this simple fictitious example. It takes about one line of code to create a new component and one line of code to connect two components together. Now, once you call the run method on the pipeline, the Psi runtime actually takes charge of executing the pipeline. So it schedules the components for execution and it starts flowing messages on these temporal streams of data. The streaming infrastructure in Psi has a number of very important properties. First of all, streams in Psi are strongly typed, right? They're based on .NET generics. You can stream any type of data. You are not constrained into only using certain specific data types. And you get things like type safety. Now, more importantly, though, is the fact that time is really a first-order primitive, a first-order construct in the Psi streaming infrastructure. So each of these messages that are flowing through the streams are timestamped not only with a creation time, which is when the component that generated that message created it, but also with something we refer to as an originating time. This time is assigned at the source when the message first enters the pipeline. So for instance, when the camera first sees an image or when the microphone picks that particular bit of audio. And the important property here is that this originating time is automatically carried forward throughout the pipeline as the message goes downstream, which means that each of these components can basically be latency aware because they know what the time is when they receive the message and they have access to this originating time information so they can find out the latency of the message. And this latency awareness throughout the entire graph enables a number of important scenarios. One of these scenarios is synchronization and data fusion. For instance, this component here, this speech source detector, knows that these two messages arrive at these specific latencies. So as messages arrive, it can buffer them and pair them according to when they happen in the world as opposed to when they arrive at the component. In fact, Psi provides a large number of primitives that support this kind of synchronization and data fusion, interpolation, windowing, all these time-related operations, and eliminate the need for the developer to think about how this exactly needs to be done, how much things need to be buffered, how things are coordinating. Rather, the developer can just use these primitive operations and compose an application and focus on the task at hand. Another important property of the Psi streaming infrastructure is that data can be easily logged. Logging is a very important aspect in these applications, a core piece of functionality, and Psi enables it in a very easy manner. You can just apply a .write stream operator on any of these streams and send the data to disk. The framework automatically generates custom serialization code, so you're not bound into any specific types. You can basically log most .NET data types. And the fact that the timing information is persisted together with the data means that we can enable another very important scenario, which is reproducible replay. So for instance, you can eliminate the sensors in an application and resurface the streams from a previously persisted store and rerun your application in a reproducible fashion, so you can tune the application, turn various knobs on the downstream components, and improve them to get the results that you want. This kind of reproducible experimentation is an important accelerator in this space. There's a number of other affordances that the Psi runtime provides, and I don't have time to go into all of them in detail here, but just as a high level, the runtime, just like the components, also has access to the latency information. So that opens up interesting opportunities in terms of how the runtime does scheduling to get pipeline parallelism efficiency and to maintain things running at steady state. It also enables developers to control how the application behaves under load. So for instance, application writers can specify on which streams information may be dropped and under which circumstances, and which of the messages can be dropped, and so on and so forth. I don't have time to go into detail into all these aspects here, but there's a lot more documentation on the GitHub site where you guys can learn more about this. Now, so far we've talked from the perspective of an application writer. Oftentimes when you develop Psi applications, you hopefully will be able to reuse off the shelf a large number of components, but chances are you will also have to write your own components that are specific to your own application. The Psi framework makes writing components also easy. So for instance, if I want to write this speech source detector, all I have to do is write a class for this component and implement two so-called receiver methods, one for each incoming stream, right? So when a message arrives on this stream, the voice activity receiver method gets called, and similarly when a message arrives from the lip movement detector, then the respective method for receiving that lip movement gets called. That's pretty much what it takes to write a component, and then from inside the receivers you can post messages downstream to send them out on the component output. Now, the Psi runtime provides a couple of other important properties here, and one of them is state protection. What I mean by that is that you can define your own state variable, like for instance this time since the person last spoke variable here, and you can touch this variable from both receivers. You can write to it and read it from both receivers without having to lock it or worry about concurrency issues. When the Psi runtime schedules the various components in the pipeline for execution, it tries to maximize pipeline parallelism, so we will execute receivers of different components in parallel on multiple threads. But it will always ensure that the receivers of a given component are executed exclusive with respect to each other. So this exclusivity is enforced automatically by the runtime, so you don't have to worry about concurrency. You can program this component as if you live in a single-threaded environment, even though when it's put in an application and run as part of a pipeline, it will run concurrently with many other components. So this is a property that simplifies component authoring, and it couples to another important property, which is isolated execution. Whenever one of these receivers receives one of these messages, it can actually modify it and edit it and touch it and manipulate it internally however it wishes. because if this message is being sent to a number of other receivers at other components who can also touch it, the SI runtime automatically ensures that everyone gets their own copy. So there's an automatic cloning mechanism implemented that, again, insulates the component writer from the intricacies of a concurrent execution environment. Finally, another important property here is that you can easily hierarchically compose subpipelines into higher level components. And this type of hierarchical composition, of course, helps with encapsulation and with keeping the code simple at the top level. But the other important property here is that when the runtime executes this, each of these individual components still run as individual subcomponents, so we still get fine-grained pipeline parallelism from a runtime standpoint. And so this programming model fosters, in some sense, using a lot of small different components that execute in parallel and avoid some of the traps of growing large monolithic components. So hopefully this has given you a sense of what are some of the main principles and affordances in the SI streaming infrastructure and runtime. And with that, I want to switch gears and talk a bit about tools. Well, in the space of tools, we've put a lot of accent on data visualization. Specifically, SI provides this application we refer to as Platform or Situated Intelligence Studio, or in short, SI Studio, that enables users to easily visualize data from collected by SI applications. So you can open one of these stores that was persisted by SI applications, and with simple drag and drop operation, create these complex composited layouts. In this case, I have a visualization from a sample application in which a user can point to various objects in the room, and the machine tries to detect and understand what these objects are. You can have timeline visualizers, so things like audio, numerical streams, speech recognition results. At the bottom there, there's a latency visualizer. You can have 2D visualizers like images overlaid with object detection results, histograms, and so on. You can have 3D visualization, so you can easily look at sort of point clouds, rotate around the image, visualize various kinds of other 3D objects like tracked bodies and camera views, and so on and so forth. You can easily navigate over time, and you can inspect various values that streams take over time. You can easily zoom in and out, and you can adjust which region of the data you're viewing. There are a number of ways in which you can navigate basically in the data, and the tool makes it pretty easy. You can also play back sections of the data, and you can do that at the regular real-time speed and listen to the audio that was recorded, or you can play back things at a faster speed or at a slower speed if that's of interest. Now, apart from all this support for visualization, another important aspect here that the tool provides is data annotation. So here someone's demonstrating actually creating annotations for which objects this person is actually pointing to. This is a very useful affordance in a lot of these systems when you're trying to either generate annotations for machine learning or maybe to tune and understand the behavior of your application. All of these visualizations can be done offline based on data that was previously pre-recorded, but also live as demonstrated here. So you can open the tool and connect to a store that is being actively written to by a live application, and the streams will show up live and you'll see what's going on moment by moment in the system. And you can even drop out of live mode and scrub through the data and then catch back up with whatever it is actually playing. The framework also has support for working with large data sets. For instance, here someone demonstrates a data set with multiple sessions. So as your system runs and you get multiple sessions, you can accumulate these in a data set. And then you can do data processing. For instance, here we're running a batch processing task for generating new acoustic features. And then the streams that get generated from this batch processing task can be visualized in line with everything else. Finally, in the long run, we're planning to develop fully interactive capabilities here where you can write short snippets of code and directly interact with and manipulate with your data from code and see it as you write in a read, evaluate, print kind of loop. So hopefully this gives you a sense of the data visualization and annotation tools that are currently available in the framework. And with that, I'm going to switch gear to components. The components currently available in the GitHub repo focus a lot on multimodal sensing and processing. So there's a number of components there for sensors, so like cameras and microphones and other kinds of sensors like the Azure Kinect or Intel RealSense. There's components for processing audio and imaging data, and there's components for doing things like speech and vision and language processing. There's also components for running machine learned models, for instance, Onyx, DeepNets, and also wrapping a variety of cloud services, Azure Cognitive Services. The idea here is that we are providing the seeds behind what we hope to be a growing ecosystem of components. I think success happens here when we're able to leverage each other's work. So we're hoping more of you will get engaged and contribute your own components in this space. The other thing I would like to say here is that while Psi is an open source framework, it's not just open source. It's really meant to be an open and extendable framework and to interoperate easily with other kinds of ecosystems. So for instance, ROS is a framework that's very frequently used in the robotics community and provides a number of important affordances. Well, Psi can easily bridge to ROS, and it's possible to create hybrid systems. For instance, imagine a social robot where navigation is done via ROS nodes and components, whereas the social processing part of it is done with Psi components. The framework interoperates with many other ecosystems. You can use ZeroMQ as a transport and various kinds of data formats to interoperate with things like Python and JavaScript and Unity and so on. And we continue to evolve this. Again, the core idea is that the framework is meant to be open and extendable. So this brings me basically to the end of the framework overview. Hopefully this has given you a sense of what are some of the main capabilities in the framework, some of the main tools, and whether this is something that might be useful and interesting in your own work. So next, to make it all a bit more concrete, we're going to go in this hands-on tutorial where I'd like to show you how to code the first Psi application. So as an example, we're going to build a voice activity detector. It's going to be a very simple one. We're going to take a rather naive, simple approach, but the goal here is just to illustrate how programming with Psi works like. So a voice activity detector basically determines when in an audio signal there is speech or not. And to do this, we're going to start by using a microphone component. We're going to capture audio with that component, and then we're going to pass this audio to another Psi component that does acoustic feature extraction. Now this component generates a number of different features, and we're going to look at one feature that's called log energy that kind of reflects the amount of energy in the signal. So the more noise there is, if someone is talking, the energy will be high, and otherwise it will be low. So we're going to just try to threshold this signal to recover basically the blue signal, the blue binary signal. That's the voice activity detection signal. And we'll do a bit of more processing on it, but that's the basic idea. Now, this is a very kind of naive way to build a voice activity detector, but it will be sufficient to demonstrate some of the capabilities of the framework. And once we do that, just so that I really showcase the fact that you can build rather more sophisticated applications, and we can quickly prototype something that's much more complex and that does bring together many different kinds of AI technologies. I want to very briefly, in a couple of minutes, talk about this other sample application written a couple hundred lines of code where a person can point to objects in a room and say, what is that? And the computer tries to determine which object is being pointed to, sends the cropped image to an object detection service, and tries to understand basically what the object is that the person is pointing to. Okay, so let's get started. I'll be using Visual Studio 2019 Professional Edition, but you can also use the Community Edition or VS Code, which also works on Linux, or for that matter, any editor of your choice. I'm going to start by creating a new project, and this is going to be a C# project console app.NET course. I'm going to hit next here, and then I'm going to call it Simple Voice Activity. As I hit create, Visual Studio will take a couple of seconds and generate a basic project structure for us. Now, there are basically two ways in which you could start coding a Psi application. One approach is to use the Psi source code. As I've already mentioned, Psi is available on GitHub, so you can go to github.com/microsoft/Psi and clone the repo. You can then build a solution where you link your application against the Psi source code and build it all together. The second approach, which is what I'm going to use here, is to use NuGet packages. These are binary packages that we provide with every release and that speed up development. As you don't actually have to build a Psi codebase in this case, you just link against these packages, and this is an easier path if you don't plan on actually modifying the Psi codebase. So I'm going to do that here, and to add these NuGets, you go to Dependencies, right-click, Manage NuGet Packages. You'll have to make sure that this Include Pre-Release checkbox is marked because the Psi NuGet packages are still in beta pre-release mode. And then I'm going to go to Browse, and the first package I'm going to look for is called Microsoft.psi.runtime. This package contains most of the core bits for the Psi infrastructure, so you'll use it in all your Psi applications. I'm going to hit Install. It brings out a number of dependencies, and then I'm going to accept this license, and the package gets installed. Now, since in this sample we'll be doing some work with audio, the other package I want to install is called Microsoft.psi.audio.windows. This package provides Windows-specific APIs and components for things like microphone capture, audio processing, acoustic feature extraction, and so on. So I'm going to install this one as well. Now, at this point, you may be wondering, how do I know which packages do I actually need to install when I write a Psi application? And this is where I'd like to point you to our documentation. So our documentation is at our website on github.com/microsoft/Psi and is accessible via the wiki. Now, on the right-hand side here, there's a sidebar with a lot of pointers to various parts of the documentation. And we'll go through some of this in a bit more detail later. But for now, I just want to point you to these two pages. The first one is a list of NuGet packages, and the second one is a list of components. The list of NuGet packages shows you all the different packages that are currently available, together with a brief description about what functionality they provide, as well as information about whether the package is running on Linux or Windows, and what kind of CPU platform the package is built for. On the list of components, you can find more detailed information about all the components that are available. They're grouped under different categories like sensors and imaging and vision and so on. And there's information about which package each component is provided in, and also a brief description about what the component does and information about the platform. So these two pages, the list of NuGet packages and list of components, can be very useful in the early stages when you're trying to discover basically what's available. But let's now get back to actually writing the application. So I'm going to start by adding a couple of using statements that will give us access to the packages we just added. So using Microsoft.psi and using Microsoft.psi.audio. Now, as we've previously discussed, Psi applications consist of pipelines of components connected to each other via streams of data. So the first thing we'll have to do is create the pipeline. This can be done easily by means of a factory method called pipeline.create, which we can invoke to get back this pipeline object. And to run it, you can simply call the run method on the pipeline. But in this particular case, I'm actually going to call this a sync version of the run method, because what I want to have happen here is I want to start the pipeline running, then I want to wait until the user presses a key. And once the user presses a key, I want to actually stop this pipeline. And inside, to stop a pipeline, you have to call pipeline.dispose. So this is pretty much all the code you have to write in order to create and run a pipeline. Now, of course, this pipeline is at this point empty. It has no components in it. So let's start next to add some of these components. And just so that you don't have to wait for me to type, from now on, I'm going to try to directly paste some code blocks that I've written, and we'll discuss them line by line. So these 3 lines of code basically create a microphone, an acoustic feature extractor, and connect the two together. The first line creates the microphone by simply creating a new instance of this audio capture component class. Every time you instantiate a component in Psi, you have to pass it the pipeline object. And in this particular case, I'm also passing a configuration parameter to specify that I would like this audio capture component to generate audio in this specific format. Similarly, the second line creates an acoustic feature extractor by instantiating the corresponding component and passing the pipeline object. And finally, the third line connects the two together by using this pipe2 operator. Now, in general, in Psi, each component has a number of outputs, or so-called emitters, that produce streams of data, and a number of inputs, or so-called receivers, which receive the streams of data. And the pipe2 operator can connect emitters to receivers. In this case, the microphone component happens to have a single output called .out, and the acoustic feature extractor has a single input called .in. So normally, this code should look like this. I am piping an actual emitter called out to the receiver on this other component called in. However, since these two components have a single receiver and on this side a single emitter, the pipe2 operator works directly over them, allowing the code to be simpler and more readable. So this is pretty much how easy it is to create and instantiate new components and connect them together in Psi. Now, before I run this, I want to do one more thing, which is to add some printing information in the console so we actually see something happening as we run this little sample. Remember that we're interested in setting a threshold on the log energy feature from the acoustic feature extractor. So here are a couple of lines that actually print that information. So from the acoustic features extractor component, I take this log energy stream, and to it I apply this stream operator called do that allows me to specify an action to be performed for every message on the incoming stream. And the action in this case is specified by this delegate provided here that basically instructs the operator to print every incoming log energy value to the console. Now, this pattern of applying operators to stream is quite common in Psi, and we'll see a couple more examples shortly. But for now, let's just run this. So what we can see is that the log energy values get displayed, and you can kind of tell that the values are low if I stay silent, and then go higher if I start talking. So let's stop this. You've noticed probably that the printouts come pretty fast, and that's because this do operator executes on the cadence of the incoming messages from the log energy stream, which in turn is generated by this acoustic feature extractor component in response to messages from the microphone component. And this one generates audio buffers on a fairly fast pace, I think every 10 milliseconds or so. So what I want to do is slow that down, and the way I will do it is by injecting a stream operator here in front of the do operator, and this is the sample operator. So I'm going to sample this whole log energy stream on a specified cadence, say about every 0.2 seconds. And that way, the next do operator will only work over these more sparsely sampled messages. Now, when I run this again, we will notice that the cadence of the printout has slowed down. So now we can more clearly read it and see that the values are relatively high when I'm talking and lower when I'm not. Okay, so the next thing I'd like to show you is how to actually persist streams to disk and how to visualize them. Data logging is key in a lot of these applications, and Psi makes that very easy. The first thing you'll have to do is to create a store in which to log this information. And in Psi, you can do this again with a factory method called PsiStore.create. And I'm telling it the name of the store and the path where to put the store on disk. And then to write these streams to disk, you simply use this other stream operator called write. So here's 3 lines that are writing the microphone stream and 2 streams from the acoustic feature extractor, the log energy and the zero crossing rate, to the actual store. I have to specify names for each of these streams. So this stream, I'm writing it under the name audio. This one is log energy, and the third one is called zero crossing rate. So when I run this again, it will behave just like before, only that now the streams are actually written to disk. Testing 1 2 3. Testing 1 2 3. Testing 1 2 3. So if we go now to the temp folder, you notice here there's a simple voice activity.0000 folder that was created, and in here there are a couple of files that all together form the store in which we have persisted these streams. The persistent system inside is optimized for throughput, and you might see multiple data files in a store like this, plus some index and catalog files. Now we will be able to actually visualize this data, and to do so we will use SciStudio. This is a tool that comes with the Sci framework. You'll have to build it actually from the Sci code base. I've already done that build, so I'm going to just go ahead and open it. So SciStudio is an app that lets you visualize multimodal data. You can open the store that we just created in the temp folder, and you can pick any of these files. SciStudio figures out that all together they form a store, so you can select any of them and open it. And the tool will display the streams available in that store: audio, log energy, and zero crossing rate. You can visualize these streams by dragging them in the visualization container in the center. So here's the audio, here's the log energy, and I'm going to drag the zero crossing rate and overlay it here with the log energy. Now, SciStudio lets you construct fairly complex visualization layouts with multiple panels and overlaid visualizers. And the structure of these layouts is displayed in this tab here. So we see we have two timeline panels. One contains a visualizer for audio, and the other one contains two overlaid visualizers for log energy and zero crossing rate. The panel on the right-hand side shows properties for visualizers, panels, and streams. So here, if I select zero crossing rate, I see the properties of this visualizer, and I can actually change colors and various other aspects. So for instance, here, I'm going to change this to a darker color because we're less interested in the zero crossing rate. Then I'm going to select log energy, and I'm going to change this to a brighter orange color and maybe increase a bit the line width. SciStudio lets you also very easily navigate over the data. You can actually zoom in with the mouse scroll wheel and zoom out. And you can click inside this panel and drag the timeline to the left or to the right. At the top, there's a navigation bar that provides some more information about timing. The entire black region at the top represents the entire store, and this gray highlighted portion of it represents the portion that's currently in view, and I can select that and move it around, so I can move the view across my store, and I can also adjust its edges to basically adjust the portion of the data that I'm actually seeing. You can also select portions of the data and play them back. Testing 1 2 3. Testing 1 2 3. And actually you can do that at different speeds. But for now, I'm actually going to remove this selection and zoom back to the level of the entire store. So what we'd like to do here is figure out what threshold we should pick for this orange stream to construct our voice activity detector. And so we'd like to inspect some of these values. And you can do so by right-clicking here and then selecting Show Legend, which will display sort of a live legend that as you move your cursor over time, it will update those values. So you can see that high values are in the range around 10 and so on, and low values are around 1. So for now, let's just pick something in the middle, let's say 7. Let's go back to the code. Now, to create this voice activity stream, I'm going to actually use another stream operator called select that allows me to transform a stream by applying a function. The function I've specified here is one that returns true if the log energy is greater than 7. The resulting stream will be a stream of Boolean values, and I'm writing that to the store as well under the name VAD. Now, before we go and run this, I want to show you another feature of the framework. Oftentimes, when you build an application, you may collect data from various sensors, like I've done here with the microphone. But then as you tune the application, instead of running it live again, what you'd instead like to do is rerun it over the same data that you just collected, perhaps many times in a row, adjust and tune parameters and see how the application responds and how you need to tune the parameters to get the behavior you want. So let's do that here. Instead of running it live again, let's run it over the store we just collected. So in the original application, the audio data was coming live from this audio capture component. So I'm going to remove this line, and I'm going to create that microphone stream instead by opening a store and opening the stream from that store. To open the store, I just use the sitestore.open method, and I pass in again the pipeline, the name of the store, and the actual path where the store has been written. And to open the microphone stream, I call this openStream method on the input store. I tell it the name of the stream, which in this case is audio, and the type of messages in that stream, which is audio buffer. Everything else stays the same. But now when I run this application, the data no longer comes from the live microphone, but actually from the store that we collected a few minutes ago. Now, of course, this store is finite, and at some point the stream of data will terminate. There it is. I'm going to hit a key again and dispose the pipeline. Now a new store was just generated, so we can go ahead and visualize that inside Studio. So if I go to Open now and go basically in the folder above, there's a new session that was generated called 0001. So if I open this store, basically this will look the same because those streams have the same values, but now we have an extra stream here called voice activity detector. So let me visualize this. Well, it kind of worked. In general, it seems to be doing the right thing, except that we have these little fluctuations up and down. And this happens because there's a lot of variance in the log energy stream and goes up and down pretty fast. And often there's small internal sort of dips or silences, which we'll need to filter out. So basically, instead of switching from 0 to 1 and from 1 to 0, every time the log energy passes that threshold we have chosen, we want to move from 0 to 1 only when the energy has stayed at 1 for a while, and similarly, from 1 we want to drop to 0 only if the energy stays below the threshold for a while. Now, in order to determine how long that should be, we need to get a rough estimate of what's the length of these drops. So I'm going to zoom in into one of these, and actually SciStudio does have some tools that let you better understand and measure time. If you click these 3 clock buttons on the toolbar, the navigator displays some additional timing information. And now if I go and select a region, then I can see, for instance, here, where is the selection end relative to the selection start. So where is the red line, in this case, relative to the green line, to the selection start. And that is, in this case, about 177 milliseconds wide. So that's the width of this interval. And just to be safe, I'm going to choose a larger value, say around 300 milliseconds. So let's go back to the code now. So I'm going to paste another couple of lines here to create basically this filtered signal. And we'll take a look at them in a second. Actually, I have a couple of small errors here because I am using some link operator, so I'll have to go to the top and add another using clause for system.link. Now, if we look back here, these errors should have gone away. Yes. So here I'm using a couple of additional stream operators. The first one is called window, and this lets me buffer a window of messages. And in this case, I'm looking for messages in a future interval of 300 milliseconds. The second operator is an aggregate operator that lets me implement a stateful computation over its input, which in this case is this window of messages. So when using this operator, I have to specify the initial value for the state of the VAD signal that I want to produce, which is false at the beginning. And then I have to provide a function. This function has actually 2 parameters. The first parameter describes the previous value of the VAD computation. As I've said, this will be a stateful computation. And the second is the buffer of messages that arrives as an input to this operator. And this function actually constructs the signal. Basically, what this expression does is it says that if the previous state was false, then all the messages in the buffer window have to be above 7 in order for us to return true. And alternatively, if the previous state of the VAD signal was already true, then we can remain a true only if it is not the case that all the messages in the buffer are below 7. In that case, when all messages in the buffer are below 7, we need to return false. And then we're writing this stream to the store as well. So let's run this one more time. And remember that we're still running over the data that we've previously persisted from the store that we collected before. Only that now we're computing this additional filter voice activity detection signal. So let's go back to SciStudio. Now I'm going to zoom out again all the way to the session, and I'm going to open the new store that was created, one folder up here. And so now we have this VAD filtered signal, so let's look at this one. Okay, so this looks better. You can tell it's not actually quite perfect, like we're still missing some regions here. But as I've mentioned already, this is a very simplistic way to build a voice activity detector. It actually gets quite a bit more complicated if you want to build something that's really robust and reliable. The reason I've shown you though this small example is mostly to give you a sense of what programming with Sci is like, and about the visualization tools that you can use, and how you can iterate and save data to disk and replay from disk to fine-tune an application. Now, looking back at code, as you've seen, you can easily construct components and connect them to each other with this pipe2 operator. And there are many other operators that are available that let you process and manipulate streams of data. We've already seen some of them, like sample and do and select and window and aggregate. There are many other important affordances in the framework. For instance, the framework has operators that deal with temporal synchronization and data fusion. Or there are ways in which you can control how the application keeps up under load. For instance, you can configure whether, when, and which stream messages get dropped if there are not enough computation resources available. Components can be organized and aggregated hierarchically into sub-pipelines, and so on and so forth. I will actually point you in a second to more resources for learning about the various aspects of the framework. Now, this example we've worked on has been quite simple, and so before we're done here, I wanted to just briefly show you another example that's a bit more sophisticated, just to highlight how quickly you can construct more complex multimodal integrative AI applications. And I want to start by showing you this in SciStudio. Now, this store was collected with an application where we're trying to determine what object a person is pointing to. Let me take out this timing information and open the new store. Now, as I've opened this store, you'll notice that because the store doesn't contain any of these streams, they appear here with this yellow exclamation mark icon that indicates they're not currently available basically in this store. They're in this unbound state. In SciStudio, you can actually save and reuse various layouts you've constructed. And in this case, I've previously saved the layout that's specific to this new application. And to load it, I can simply select it from this drop-down list. Now, as you can tell, this is a somewhat more complex visualization layout than what we've worked with so far. Now, in this application, we have an Azure Kinect camera that's looking into a scene here. You can see the point cloud visualized, and this is a 3D visualizer. You can rotate around it. And we are doing body tracking and determining the direction that the person is pointing. We're intercepting that direction of pointing with a depth map. And we're taking this point and projecting it back into the RGB color camera and cropping a region around it. That's the image you see over here. And this image is being sent to Azure Computer Vision Service to perform object detection. The results from object detection are overlaid over the image. Finally, we're also using an audio capture component and voice activity detection, and we're cropping the audio in those regions and sending it to Azure Speech Recognition, which gets us back speech recognition results. The idea being here that a person could point to an object and say, "What is that?" and the machine would figure out what they're pointing to and respond accordingly. Now, obviously, an application like this is processing a variety of data streams, including depth, images, and audio. And we've glued here many different components, from Azure Kinect to custom-written gesture detection code. We determine, for instance, when the person is lifting their hand, this white signal indicates that, and only crop the region and try to figure out the target at those moments. And we integrate this with cloud object detection and speech recognition. Psi enables you to write such multimodal applications that leverage many AI components very quickly and in a very compact manner. And let me just really quickly give you a peek at the code for this application. So the patterns in the code are quite similar. We're creating a pipeline and a store to write the streams to. We're instantiating audio capture component, and in this case, for instance, Azure Kinect component that will provide streams for images and tracked bodies and so forth. And we're doing stream computations via a number of stream operators. One of the patterns that I wanted to quickly show you here is that you can write actually your own stream operators. Bodies here is a stream of bodies produced by the Azure Kinect camera, and this get closest body is a custom stream operator that I just wrote for this specific application. We've seen so far how Psi has a large number of operators that are generic, that operate over generic data types. You can implement your own operators. For instance, this one is implemented over here, and you implement them as an extension method for a particular kind of stream. So every time I have a stream that contains a list of Azure Kinect bodies, I can apply this operator. And the code of the operator is relatively compact, but it can be used as one line, which makes this readable here at the top level. And basically down below, we do some other computations with these streams. We instantiate the object recognizer and provided the Azure subscription key, and similarly with the speech recognizer. Basically, this whole application up to instantiating and running the pipeline is pretty much at the top level 100 lines of code. Now, there's these stream operators that I've just described that add maybe another 100 lines of code or so. But as you can see, this application can be written in a very, very compact manner. So hopefully between this example and the one we worked through in more detail before, this is giving you at least an initial sense of what working with Psi is like. Now, we didn't have time here to go into a lot of detail, and there's actually quite a bit more information available on the website. So next, I'd like to point you to some of that and orient you a bit around our documentation and resources. So as I've mentioned before, our documentation is accessible from the GitHub project wiki pages. And the sidebar on the right-hand side guides you through it. There's information about how to use and build the framework, either how to build new applications with NuGet packages or how to actually build the entire code base. And if you want to get started, the best place to start is the brief introduction tutorial. Now, this tutorial covers some of the topics we've already covered, but at the same time goes in a bit more depth and also talks about other topics, for instance, synchronization, and provides a number of pointers to additional readings and documentation on various topics that are relevant. So it acts basically as an entry point in the framework. And you can go through it at your own pace. Following this, I would recommend going either through some of the samples or through the tutorials. We have a number of samples, and they're described here. So there's a brief description with information about whether the sample runs on Windows or Linux. And also some of these samples have walkthroughs, so more documentation about how the sample was actually constructed. And again, these pieces of documentation point you to additional information and link into additional topics that you can explore in more depth to learn about the Psi framework. Going back to the wiki, the tutorials are also a good place to start reading as they provide a bit more of an in-depth overview of certain areas of the framework. So for instance, I would definitely recommend reading the tutorial on basic stream operators, which explain the family of operators provided by Psi. The tutorial on writing components that explains how to write new components. I haven't shown you any of that here. And other tutorials, for instance, understanding how the pipeline actually gets executed, or delivery policies which control the flow of messages and permit you to drop messages when the application may not be able to keep up. There's other topics on stream fusion and synchronization, merging, interpolation, and so on. So feel free to peruse all of these documents. They provide useful information about how to use the framework. There's also documentation for a number of more specialized areas under other topics. So for instance, how to do remoting. Psi supports constructing systems that are distributed, that talk to each other across machines, or how to bridge to other ecosystems like Python or JavaScript or ROS. And there's a number of other more specialized topics that are of interest to probably a certain population of developers. In general, there's quite a bit of information on the wiki. We'll continue to add more documentation and organize it in a way that's approachable. But also, if you feel there's a part of the documentation that's perhaps underdeveloped or you don't know how to do something, don't hesitate to just file an issue on the GitHub site, label it with documentation tag and say, hey, can you guys document this part more, and so on. So I think this brings me to the end of this brief dive into how to program with Psi. And let's go back to the slides. So hopefully this coding session has given you a more concrete feel for what working with Psi is like. I hope you'll also be able to tell whether something the Psi is something that's interesting for your own work at this point. And I'd like to talk a little bit about how you might get involved if you choose to do so. So Psi is built as an open source framework, and we are looking for growing a community around it and finding more contributors that can help us push this to the next level. So what are the various ways in which you may contribute? Well, of course, use it and let us know how you use it and what you find. Don't hesitate to report any issues you find or bugs. If you think some important feature is missing or some documentation is missing, also don't hesitate to file issues on that. We welcome contributions of many different kinds, from finding bugs and filing issues, all the way to writing new features, and especially developing new components. Success, I think, comes only in this space if we're able to leverage, as I said before, each other's work. So we're looking to grow the component ecosystem. A number of our early adopters have already started building their own components, and that's great to hear. Would like to see more of that going on. And ultimately, if you find it useful, tell others about it. We'd like to spread the word. And with that, thank you so much for listening to this presentation, and we're ready to go to the live Q&A session. Hi, everyone. Thanks again for tuning into the webinar on Platform for Situated Intelligence and to the live QA session that we're starting now. I know there were a little bit of trouble at the beginning. I apologize for that. There were some technical difficulties with the logins. You might have missed the first few minutes of the presentation, but it will be available also on demand after the fact, probably in a couple of days or so. So you can go revisit that if you need to. I hope you found the presentation informative. And as I mentioned at the start, two of my colleagues, Sean and Ashley, are joining me for this live QA session. And before we start, I let them briefly introduce themselves. Sean?
Hey, everyone. I'm Sean Andrist. I'm a researcher in the group working on Psi. And Ashley?
And hey, everybody. I'm Ashley. I'm one of the engineers also in the research group working on Psi.
Cool. So before we dive into some of the questions, there are a lot of great questions. Thank you so much for all the questions you guys have sent. We've tried to answer some of them on the spot, and we'll address some other ones right now. Before we do that, I just wanted to mention that since we recorded the webinar, we also pushed out a new release. And a couple of you were asking about the what is that sample that was demonstrated and whether that's available. And I wanted to say that that we are shortly going to make that available in the Psi samples repo together with so both examples actually that we worked through in the coding part of the webinar will become available. And just keep an eye on the repo, and you'll see those updates. We're also working on a longer kind of archive paper that describes the framework in more detail. That can be a good resource for those of you that are interested to take a sort of a more in-depth look into the inner aspects of how the framework is built. So stay tuned. We'll post that information on the repo. And now let's go to the Q&A. And here I wanted to start with, like I said, we got a lot of really good questions. I want to start with a question that we actually often receive that arrive here, but we also received in other places, which is, what's the relationship between Psi and ROS? How does Psi relate to ROS? and how does it relate to, can I program Psi, for instance, with Python or other ecosystems? And I'll let Ashley say a few more things about this.
Okay, yes, this is a question we get a lot. Some people ask whether there are language bindings for non.NET languages for Psi. And there isn't exactly language bindings for doing Psi-like things in other languages, but we can communicate with other languages, such as Python, such as JavaScript in Node.js, etc. The way that we do it is through an inter-process communication mechanism. Inside of Microsoft.psi.interop is a bunch of libraries and tools for doing this. We can encode Psi messages to more ubiquitously available formats such as message pack or JSON or CSV, or you can bring your own format. It's an extensible system. And then we can transport those over a message queue, 0MQ. There's libraries for that for Python and for JavaScript. And in that way, you can bridge between a Psi application running in one process and, say, a Python application running in another. There's a good sample walking through this. If you go on the wiki under other topics, bridging to Python, there's a good sample that shows exactly this, a Psi process talking to a Python process, shuttling messages back and forth, maintaining the times as that happens so you can still do joins and things like that. That's a good example. I should note that if you actually are trying to do communication between two Psi processes, that can also be done, but I would suggest using another system that we just call remoting. That uses the inbuilt super efficient serialization system that Psi has built into it, and it maintains the fidelity of the types and things as these messages go back and forth. And so that's kind of the suggested way to do inter-process communication between Psi apps, if it's actually Psi on both ends. Similarly, working with ROS is a very common thing, and the solution is somewhat similar. ROS is a lot like Psi in that it's also an actor model with loosely coupled little cohesive components that communicate through message passing. By default in ROS, the communication of messages is over TCP or UDP using their own message serialization protocol. And so we interface with ROS by doing the same kind of thing. We can serialize Psi messages as ROS messages using that protocol. And we have a whole ROS bridge built for joining a ROS graph, essentially. You can write Psi components that can become nodes in a ROS graph. They can talk to the master, publish and discover topics, discover other nodes, negotiate peer-to-peer connections, and serialize the messages back and forth. This is for ROS1, actually, the ROS1 protocol. We may someday in the future release something for the ROS2 protocol. In the meantime, there are shims in the ROS ecosystem for shimming ROS2 components to ROS1 protocol. And again, there are good examples in the wiki, again, under other topics, bridging to ROS. It shows a couple of good samples. One of them in particular just uses the ROS turtle sim, so you can just run that on a laptop without having any hardware, which is nice. And it has links to the more in-depth documentation on how the bridge itself actually works. So I hope that answers that question. Back to you, Dan.
Cool. Thanks a lot, Ashley. Another question that we sometimes that I saw in the link here was, can the visualization tools that we demonstrated be used offline with previously collected data streams? And certainly they can be used with data you have collected with a Psi application, but this is a request we've gotten in the past about bringing your own data that might be in different formats into the Platform for Situated Intelligence Studio and being able to visualize it. And recently, is actually in one of the recent releases, we have added that capability. So there's an interface that you would have to implement to basically create your own importer that lets you bring your data that might be stored in some other format into the Platform for Situated Intelligence Studio and do all the visualizations. We actually implemented ourselves, apart from the support from our own Psi stores created by Psi apps, support, for instance, for opening WAV files and just dragging them and bringing them into Psi Studio. And you can do more. And this is, again, an area where we're trying to be an extensible platform, and we're hoping to get community contributions and build these capabilities more and more, and interface and interop with more data formats, more ecosystems. I think hopefully that addressed that question. There is another question about whether it's possible to write your own custom stream operators, and combine them with existing things like the windowing operators and so on. That's also certainly possible. It's definitely the way to program with Psi. Often you find yourself having to write your custom processing operator. Psi in the infrastructure provides a pretty wide array of operators that work over generic streams that let you do a lot of basic operations over streams, including simple operations that involve time, like synchronization and so on, like we discussed. But oftentimes you will need to write your own custom specific, and it might be a simple operator that takes a single input and produces a single output. And when you write that, you can leverage inside it other existing operators. There's a way to write these composite components, we call them, or it can be a complex composite component that has many inputs and many outputs. The idea is that we would like to be able to reuse as much as possible, use the existing components that you find in the ecosystem and write new components that are specific to your application where you don't find them already. And we, again, like we've mentioned before, we hope to engage with the community and we hope to grow this ecosystem over time with contributions so we can better leverage each other's work. I'm not sure if there are any other questions or if we're slowly getting towards the end of this Q&A session. Sean and Ashley, have you seen some other question in the chat box?
Dan, do you want to talk a little bit about how someone asked about like how elbow angle was calculated and what is that? And I don't know if you want to speak a little bit more about that, and because that was with a custom operator, basically.
Yeah, and I'm sorry you guys don't see. Look, the sample we'll post the sample shortly on the GitHub repo, and we'll have a kind of a really nice walkthrough that walks you through how exactly that sample was built from the beginning to an end, and points to various other relevant pieces of documentation in the framework. But certainly for that elbow angle computation is just it's basically a custom stream operator that takes in a body, and so it takes in a stream of bodies essentially and produces a stream of elbow angles. And essentially inside that operator, you just look at where the joints are for the wrist, for the shoulder, and for the elbow. And there are simple ways to do sort of 3D angle computations and compute that on a stream. I think the sample will demonstrate it illustrates in a relatively compact, like I said, it's a couple of hundred lines of code, it illustrates in a relatively compact manner the power of that you can get by quickly combining a number of these stream operators, using a lot of existing ones and writing your custom ones where you need to. So I think as soon as that, probably, hopefully by next week or sometime, soon, we'll be able to push that up on the repo. You guys can have a look. We're looking also, I should say, for, I mentioned this already, I think in the presentation, for feedback. So wherever you find, we're not able in this session to answer all the questions, but if you have specific technical questions about the framework, please do not hesitate at all to file issues on the GitHub repo. We're happy to engage and answer questions you might have around this. I think that brings us close to time, so we'll probably stop here. Thanks again, everyone, for attending, and we really appreciate your participation and interest in this. If you want to learn more, there's a list of resources in the resource list on the right of your screen. It has pointers to the GitHub site and the blog post that we've recently posted that gives a high-level overview of the framework. And as I mentioned before, we're hoping you'll engage with us via GitHub in growing this to the next level. Thank you so much.